All right, 7.8.3 is comparing populations, and this is going to pull from some of the vocabulary and the concepts that we learned last week, where we kind of dipped back to 6th grade just to make sure that we understood some of the concepts that have to do with statistics, which go into today's lesson. So you'll need to remember what mean and mean absolute deviation are, what median and interquartile range are, and then also how to describe the shape of a distribution, because they'll all kind of come together in this lesson. So we're going to talk about comparing populations, where we have a set of data, and comparing the sets of data. All right, now if we have a symmetric distribution of data, so remember a symmetric distribution looks something like this, where we have sort of intervals of data or pieces of data that all lead up to one data point. So they're kind of symmetric, not to one data point, but kind of they kind of mirror one another on either side. So it goes up kind of in an even fashion and then back down in an even fashion. So we would say the data is symmetric. It doesn't have to be exact, but generally. Symmetric distribution also can look like this, where maybe we have big pieces of data on either side, but still it is symmetric on either side of the center. So kind of going up gradually. In this case, it goes down and then down toward that center line. So those are symmetric. If you have a symmetric distribution, then you need to compare the data using the mean or the mean absolute deviation. And so this is if you have two populations with symmetric distributions. On the other hand, if you have two populations with skewed distributions, so perhaps we have one population and the data looks like this, something like that. Okay, we would say that this data is skewed left because the tail is going to the left. As long as at least one of the data, one of the populations are skewed, we don't use the mean and the IQR to compare them. We don't use the mean and the MAD. Instead, if one of the distributions is skewed, or if they're both skewed, we use the median and the interquartile range, or IQR, to compare the data. Now, the other thing that you need to remember in terms of vocabulary is that the mean and the median are both measures of center. Okay, the mean and the median both give us an idea of the measure of center. So if you're asked to compare, two populations using their measures of center and their measures of variation, then you need to determine whether you're going to use the mean and the MAD or the median and the IQR. So the MAD, the mean absolute deviation, and the IQR, the interquartile range, those are measures of variation. So we use center and variation to describe data sets and to compare populations. As a reminder, a box and whisker plot, I'm going to go back. A box and whisker plot is this, and it's going to come up in this section, so it's important that you know what it means and how to read it. We didn't talk a ton about these in the last chapter. We saw them a little bit, but I want to make sure that we're all very clear. A box and whisker plot makes it really easy to see, especially in a skewed distribution, the median. The median is always this middle line with a dot down in the middle of the box. It makes it easy to see the first quartile and the third quartile. And remember, if we have the first and third quartile, we can find the interquartile range by doing Q3 minus Q1. We can also see the range of the whole data set because we can see the biggest value and the smallest value and subtract those. What the interquartile range does is the box and whisker plot does is it shows us the distribution of data in quarters. So this first section shows us the first 25% of the data. So that whisker shows us 25%. The box shows us 50% of the data, right? The middle two 25s or the middle 50%. And then the last whisker shows us the final 25%. Okay? Now, we can also describe the shape of data from a box and whisker plot. We find the median, and then we look at which way the tail of this data would go. So if we were going to sort of look at the median, we see that there is a lot of data on the left side of the median and less data, on the right side of the median. So we would call this shape of this distribution, we would say it is skewed left. Because most of the data is to the left of that median, right? It's skewing to the left. So you can see distribution of data also in a box and whisker plot. Here's an example. So this one says 2 data sets contain an equal number of values. The double box and whisker plot, which is what this is, it's 2 different box and whisker plots, showing the data in these 2 different data sets, set A and set B. Notice the box and whisker plot, and it will always be like this, is always set above a number line so that you can see corresponding, for example, the median in data set A, there's a line there above the line of 60 on our number line, so our median is at 60. Or the median in data set B is above 90 on the number line, so the median is at 90. So the box and whisker plot shows us on a number line all these different values. We can see the median, we can see Q1, we can see Q3, we can see the greatest value, the smallest value, etc. Here's what it's going to ask us. It says compare the data set using measures of center and variation. So it doesn't tell you which one you're going to use. We have to use the idea that the characteristics of the distribution guide us toward which ones to use. So let's look at the data. First of all, if we look at set A, we see our median here, and we see the data going this way. The tail is going this way. So we would say that this data set is skewed right. Data set B, here's our median, and then we have our tail going to the left. So this one is skewed left. These are both skewed. And remember, when we have skewed data, we want to use median and interquartile range. So we'll use median as our measure of center and IQR as our measure of variation. All right, so let's come back to this. I'm going to erase these. So now we know, since we have skewed data, we're going to use median. So I'm going to do set A. Actually, let's do it in blue so it matches. Set A. Let's find the median and the IQR. That's median is our measure of center and IQR is our measure of variation. We can see the median and the IQR just by looking at the box and whisker plot. The median is always this middle line. So the median of data set A is at 60. And then the interquartile range, we can take our Q3, which is here, 80. And our Q1, which is here at 30. And we subtract 80 minus 30. The interquartile range for set A is 50. Then we'll do the same thing for set B, because we're going to compare these with the same measures of center and variation. Okay, so same thing. We can look at the box and whisker plot to see the median. And in this case, the median of set B is at 90. And the interquartile range, we find Q3, which is 100, and Q1, which is 80. And we get that our interquartile range, 100 minus 80, is 20. So if we compare these, we can see that the median of set B is higher, but the interquartile range is smaller. So a lot of the data is closer together in data set B because the IQR is smaller, but the median is higher. So we have a lot more small, like lower value data points in set B because it's all sort of concentrated on the left. And that's because we said it was skewed left. And then the opposite is true for set A. Our median is lower but the interquartile range is higher. We have a lot more spread out data in set A. Using the same box and whisker plot, then we go to question B, which says, which data set is more likely to contain a value of 95? So if we find 95 on our number line, and we sort of draw a little line up, we can see that 95 in data set B is going to be somewhere in this interquartile range. And this is the middle 50% of all the data. So there's a lot of numbers in there. It's very likely that one of them is 95. Versus when we look up at our whisker, there's not a lot of data along this whisker. It's very spread out here. So it is less likely that one of those numbers is 95. Is it possible? Yes. But is it likely? Not as likely. So it's more likely that data set B, would contain the number 95. Okay? Because the data is more concentrated in the IQR, so in that 80 to 100 range. And then question C asks us, which set is more likely to contain a value that differs from the center by at least 30? Now this is going back to some of our vocabulary. If something differs from the center, we are referring to a measure of variation. Differing from the center, it's either going to be the mean absolute deviation or the IQR. And in this case, we had two IQRs. Remember, the IQR of data set A was 50, and the IQR of data set B was 20. That means data set A has variation from the center by about 50 for most of the data points. Data set B has variation from the center by only about 20. So if we're asking which one contains a value that would differ from the center by at least 30, it's got to be set A, because the interquartile range is bigger than 30. So there's a lot of data points that are differing from the center by over 30, up to 50 away from that center. So we would say data set A is more likely to contain a value that differs from the center by at least 30. All right, you can compare populations with similar variabilities by writing the difference in measures of center. So difference, remember, means subtract. So we're going to subtract the measures of center, and then we can write it as a multiple of the measure of variation. So I'll show you how to do this. And the way that we're going to do this, the little formula that we can use is first we'll find the measures of center. So we have to look at the distribution. We'll either subtract the means or we'll subtract the medians. And then we'll divide by the mean absolute deviation or by the IQR, depending on which one we're using. In these situations, your mean absolute deviation, your MAD, or your IQR will be the same. You'll just have slightly different measures of center. So you're going to have a similar MAD or a similar IQR, a measure of variation. Okay, so you'll subtract the measures of center, and then you'll divide by that measure of variation. And then you'll get an answer, and that's going to help us answer some statistical questions, which we'll talk about in our example. All right, so example 2 says, express the difference in the measures of center as a multiple of the measure of variation. So we're just going to follow this formula that we did on the last page. First, we're going to describe, we have to find the measures of center and the measures of variation, and then we'll plug it into that formula. Find the difference, divide by the measure of variation. These data sets, I would say, are fairly symmetrical. If we sort of draw a little line of symmetry here, these are both kind of reflections of each other, which means because they're symmetrical, we are going to use the mean and the mean absolute deviation as our measures of center and measures of variation. So we need to find the mean for data set A by adding together all of the data points. So let's do this. We've got, try to do this slowly. You're going to use the number line for this. So for data set A, we've got one value at 20, two values at 30, so 60, two values at 40, which is 80, three values at 50, 150, three values at 60, 180, one value at 70, two values at 80, 60, 160, and one at 90. So to find the mean, we'd add these all up and divide by the fact that there are 15 dots. When we add them all together, we get 810, and then we divide by 15, and that'll give us our mean or our average. All right, so we get that the mean is 54 for set A. And then I'm going to erase all these. And we'll find the mean absolute deviation. So remember, the mean absolute deviation tells us how far each of the data points is away from the mean. So like for this first piece of data, this is at 20 in set A. 20 to 54 is 34 places, right? 20, 30, 40, 50. So that's 34 away from the mean. So if we add these all together, we've got one piece that is 34 away, and then those two dots at 30 are 24 away, so we'll do 2 times 24. The two dots at 40 are 14 away, so 2 times 14. The three dots at 50 are 4 away from the mean, so 3 times 4. The three dots at 60 are 6 away from the mean, right? 54 to 60 is 6 units, so there are 3 dots, so 6 times 3. 1 unit that is 16 away, so 70 is 16 away from 54. 80, we have 2 dots at 80, which are 26 away from 54. And finally, 1 dot at 90, which is 36 away. So if we add all of these up, we end up with 244. And then we divide again by 15 because there are 15 units of data, or 15 dots in this dot plot. So we get 244 divided by 15 is approximately 16.27. What we're going to do here is round to the nearest whole number. So 16.27 to the nearest whole number is about 16. So we'll call our mean absolute deviation 16. Okay, then we're going to start again and do the same thing for set B. So we need to find the mean of set B. So we've got 3 dots at 0. So 3 times 0 plus 1 times 10 plus 2 dots at 20, 2 times 20 plus 4 at 30, 4 times 30 plus 2 times 40 plus 50 plus 2 times 60. So that's going to give us our total. When we add all of those up, we get 420. There are 15 red dots in set B, so we're going to divide again by 15. And our mean of set B is 28. That leaves us with the mean absolute deviation. So now we're going to look at each dot and see how far each dot is away from the mean. And then divide by 15 again to find the mean absolute deviation. So 0, there are 3 dots at 0, and each of those is 28 units away from our mean. 1 dot at 10, that's 18 units away. 2 dots at 20, which are 8 units away, so 2 times 8. 4 dots at 30, which are 2 units, so 4 times 2. 2 dots at 40, 12 units away, so 2 times 40. 50 is 22 units, and 60 is 32 units away from our mean, and there are 2 dots. So we add all that up, being super careful with your calculator. It does not do order of operations, so you need to be super careful and systematic when using the calculator to try to solve these. Okay, when we add those all up, we get 236, and then we're going to divide by those 15 data points, those 15 dots, and we get 15.73. And again, we're going to round this to the nearest whole number, which is also 16, and that's what we want. right? In these kinds of problems, when you're asked to do this, your deviation, or you might have it in IQR, your interquartile range, those will be the same. Your measure of variation will be the same, but your mean or your measure of center will be slightly different. So then to finish up this question and to answer it fully, it says express the differences in measures of center as a multiple of the measures of variation. So what the last step is we subtract the means. 54 minus 28 is 26. And we divide by the measure of variation. And our measure of variation for both of these was about 16. So when we do that division, we get that this is approximately 1.6. And that is your answer. That is your expression of the measure of center as a multiple. So we would say that the measure of center, 16, is about 1.6 times smaller, or the measure of center, the means, are about 1.6 times bigger than the measure of variation, okay? What this means is that it gives us a measurement to determine whether something is significant, like statistically significant. So in the last example, because that difference was only 1.6 times bigger, it has to be at least 2 times bigger for the difference to be significant, to have statistical significance. So in the last example, it was only 1.6, which is less than 2. So if you were asked, is this significant, you would say, no, it is not. But if you did another problem and maybe you got, 3.7, yes, that would be statistically significant, the difference, because it is bigger than 2. So 2 is our cutoff there for something being significant or